it's not perfectly oriented.
Exactly.
True power.
All right, power triangle. You got true power on the bottom. This is volt amps. This is all right. So your true power for your generators, motors, what's actually using the power, okay? Your volt amps is the power that supplied here to make it go, to make it run. Magnetized power is the lost power. So this angle right here, that's power factor. So the bigger this angle is, and it's backwards as far as we talk, because we want a higher power factor, but on the power triangle, you want a lower power factor.
Yeah, that makes sense.
You want to reduce the magnetized power.
Magnetized power would be power that's being lost to the magnetic field around motors and stuff, around the wire itself. And what about ground?
The
Is that
closer you can make the angle of the volt amps to the machine, the less you're going to have here. So the only way to do this is to add what's the sign for it? That's the sign for capacitance.
Okay.
If you add capacitance to this side of the triangle, you're lowering this angle. So now it's here. So you have reduction in magnetized power in VAR. So what we're doing, we're coming up with a formula. If we know the power factor going in, and we have a target power factor we want to reach, based on this angle, we're going to develop the formula to tell you exactly what the product's going to do beforehand, before we ever put it in.
That's why when you do you determine, I lost the thought, but when you're calling it in as far as what the panel says, and then you multiply it by your factor number, you know what those capacitors will do with that capacitor, the factor number, and that's how you get that angle.
We're analyzing the capability of that panel by taking total breaker amps.
Okay.
And then we have assumptions in our formula to determine how much capacitance we need to add to that panel to lower this angle.
And the capacitance are the
Capacitor
MOV,
bank.
yeah.
capacitor bank?
Capacitor banks.
But what we want to do with this, we can take those assumptions out. And we know exactly what capacity, how much kVAR we need to add to the system based on these.
Well, but that's all contingent upon how accurate your power factor reading is, which is where the metering really comes in.
The meter's going to tell us these values over a true 30-day average.
Yeah.
And we can take that data, plug in the formula for kVAR, and the formula will equal exactly how much capacitance we need to add based on these values to minimize this angle.
Yeah. So once again, the metering becomes the real critical.
Yeah, you can't do it unless you have a true picture of what these are, highs and lows and averages.
You can do it, but it may not have an effect. I mean, if you come in with the box.
Yeah, because if you miscalculate now, either way you're gonna manipulate this angle. If you calculate correctly, you're gonna lower it. If you don't calculate correctly, possibilities are it doesn't change at all, the angle's unaffected, or the angle goes the opposite.
How would it go
You make it
opposite?
more
How could it?
oversized? You
Oversized.
oversize it. Because the oversized, if this isn't correct and this is oversized, it's going to have the opposite.
What does
effect.
VAR stand for?
Volts, amps, reactance.
Volt amps reactance. That's what the capacitor does, is VAR?
As far as in layman's terms, KVAR is lost. The lost power in electrical system. You've received so much power to do a job. The power you didn't use, that was wasted,
That's your
that's
KVAR.
rated in KVAR.
Kilowatts of,
Why, you have a problem walking lately?
okay.
Well,
That's funny.
we'll talk to you later. Unless you got something
I've
else.
seen it on the old system, it was hilarious. You'd go like this, and then it'd be like, and you're like, oh.
It's like flying a plane.
Hey, Sean, thank you for that.
No problem.
Appreciate that.